Hi, everyone. My name is Clara Deck. I'm with the NOAA Climate Program Office. I'm excited to kick off this new series that we're doing with a webinar featuring current and recent NOAA Climate and Global Change Postdoctoral Fellowship participants, or C&GC. C&GC is sponsored by the Climate Program Office and managed by UCAR's Cooperative Programs for the Advancement of Earth System Science, or CPAS. So starting with this webinar, we will be featuring one C&GC fellow per month, sharing their research. Today, we're really excited to be starting off this series with Robert Fajber. He has received his PhD from the University of Toronto in Physics and Atmospheric Science, and he went on to join the C&GC program as a fellow studying atmospheric sciences at the University of Washington, where he still is. His talk today is titled Evaporation Links the Hydrologic Cycle and Global Heat Transport. We'll have time at the end for questions. You can enter them into the question box within the GoTo at any time, or at the very end during the Q&A session, you can use the raise hand feature. And with that, I will hand it over to Robert, and he will be driving the slides today. So thank you so much for joining again, and enjoy the webinar.
All right, thanks everyone for coming. It's a real pleasure to be here speaking with everyone. And I should mention before I start that this work is in collaboration with a few people, Kyle Armour and Aaron Donahoe, who were my hosts during my fellowship, and Zoe Reagan, who's a PhD student at the University of Washington. So before I get into it, I just want to start by showing a conceptual picture. If my slides will advance. Oh, there we go. Okay, so to start off, I just want to show a picture of the global water cycle, because to me, this is kind of the basis for how we think about things. I'm sure many people are familiar with this picture. You have evaporation from oceans primarily, but also some over the land. And that adds water vapor to the atmosphere, which moves around until eventually it's able to achieve saturation at somewhere in the atmosphere. And then you get condensation, followed by precipitation, and that water is then returned to the surface. So from the perspective of water, the water cycle is moving mass, right? We're taking mass from the ocean, usually, and adding it to the atmosphere, and then that mass gets removed from the atmosphere and put back into either the land or the ocean. So from a water perspective, the water cycle is moving mass through the atmosphere. But there's this second perspective that's also really important to think about, which is that every time we move mass from the ocean to the atmosphere and then back to the surface somehow, we're also moving energy around. And a big focus of the talk is kind of going to be comparing these two different perspectives. I just want to talk about this one for a little bit first. So from the perspective of the global energy cycle, what happens is that you have incoming solar radiation at the top of the atmosphere, and some of that gets absorbed or reflected by the atmosphere, but about half of it goes into the surface. And of that half that goes into the surface, about half of that goes into driving evaporation. So about 1/4 of the total insolation gets used to drive the water cycle. And so what happens is that solar radiation hits the surface and then evaporates water vapor, which cools the surface. But that water vapor that then gets added into the atmosphere, whenever it's condensed, you're going to release latent heat into the atmosphere. And ultimately, that latent heat release in the atmosphere has to be balanced by long-wave cooling somewhere else in the atmosphere. So from an energy perspective, what the water cycle is doing is taking energy from the surface, adding it to the atmosphere, and then condensation is basically converting that latent energy into thermal energy, which then has to be balanced by long-wave cooling somewhere else in the atmosphere. So from a water perspective, we're taking water from the surface, putting it into the atmosphere, taking it out of the atmosphere back into the surface. From an energy perspective, what we're doing is we're taking energy from the surface, putting it into the atmosphere, and then long-wave cooling is balancing that energy that we've added to the atmosphere. And so every time we cycle water through the atmosphere, we're actually also doing an energy cycle. So there's energy coming from the surface, going into the atmosphere, and then being removed through long-wave cooling. And so these two perspectives kind of give us contrasting ideas about what should be happening to the energy cycle. But of course, this isn't all spatially homogeneous. A lot of the different components of the energy cycle are happening in different places. So you can see on my little schematic here. So in the tropics, you're getting more energy in than energy out. And in the extratropics, particularly the poles, you're emitting more energy through long-wave cooling than you're getting from shortwave. And so to balance this, what you have is heat transport. So heat transport is basically moving energy from regions that are taking in too much energy to regions that are losing too much energy. And so schematically, that's just what we're showing here. And you can see a curve. So this would be if instead of having just two boxes, we broke up all the different latitude bands to a little box and did this calculation. And this black curve is the total heat transport combined between the atmosphere and the ocean. But of course, some of this is in the atmosphere and some of this is in the ocean. And so you can think that what the surface fluxes really do is that they partition the total heat transport between the atmosphere and the ocean. So where we have lots of surface fluxes into the atmosphere, we're losing energy in the ocean and gaining energy in the atmosphere. And so what that does to the partitioning of atmospheric heat transport and ocean heat transport is that it causes the ocean to transport less heat and causes the atmosphere to transport more heat. Because you're taking energy out of the ocean and putting it into the atmosphere. And same, if you were to somehow lessen the surface fluxes in the tropics, you would have less energy going into the atmosphere and more staying in the ocean. And so you would change the partitioning and weighting it more towards the ocean and less towards the atmosphere. So, just based on the numbers I've shown before, you kind of expect that evaporation is doing a lot of work in setting this partitioning. And you can see the partitioning here just for some observations I have. And the red here is the atmosphere and the blue is in the ocean. And so you can see that the ocean is doing a lot of the heat transport in the tropics and the atmosphere does the bulk of the heat transport in the extratropics. But ultimately, this partitioning is going to be set by the distribution of surface fluxes. So if there's more tropical heat flux into the atmosphere, there's going to be more atmospheric heat transport and less ocean heat transport. Okay. So, from those kind of schematics that I've laid out, you'd say, okay, well, so we have this water cycle and this energy cycle, which are really linked together. And we also know that this has some spatial distribution, so we expect this is going to impact heat transport. And so I've kind of divided my talk into three parts. In the first, I'm going to just do some really simple calculations to try to isolate this heat transport and find just the component of heat transport that's related to the cycling of water through the atmosphere. In part two, we're going to use a bunch of different models to try to understand the role that evaporation plays in coupling the ocean and heat transport together. And I've got some experiments from some idealized models, some less idealized models, really runs the whole range. And then in part three, we're going to take a step back and say, well, this theory is really nice, but how well do we actually know global evaporation? And what does that mean for heat transport? And how does this help us understand the biases? Okay. So this is sort of a standard textbook picture you would normally see. On the left here, I'm showing the energy input, and the black line, the total energy input. The blue line is the moist energy input. So this is regions that are gaining and losing water vapor. So you see that the subtropics, there's more evaporation than precipitation, so we're gaining water vapor. The deep tropics, there's more precipitation than evaporation, so we're losing water vapor. And then the gray line is showing where we're gaining and losing dry energy. I should say this is data from the CMIP6 historical ensemble mean. And then on the right here, what I've done is I've taken each of these components separately and converted them into a heat transport. So the black is the total heat transport of the atmosphere. The gray is the dry heat transport, so the heat transport just from dry air. And the blue is the heat transport just from moisture moving around in the atmosphere. And you can do this calculation because you know that in steady state, the energy surpluses and deficits have to be balanced by a net transport of heat. Formula down here is showing. And one thing that's really interesting about these curves is you see that there's strong compensation between the dry and the moist. So especially in the tropics, you have moist air moving towards the equator, and you have dry air moving away from the equator. And so you have these opposite heat transports that's occurring. And one big question that comes up is, well, why is this transport? Why is there so much compensation between the moist and dry transport? Is it just a coincidence that our atmosphere is structured this way, or is there some deeper reason for thinking about this? And what you can do is you can actually take apart the dry component separately. So here what I'm showing now is just the decomposition of just that gray line from the last slide. And on the left, I'm showing the net energy input. So the gray line is exactly the same. The purple line here is the energy input into the atmosphere coming from condensation. The red is the energy input coming from sensible heat flux of the surface. And the orange is the net radiation. So this combines the short wave and long wave into one. And what you see is that if you look at the spatial structure, well, sorry, I should say first on sort of a global scale, you see that most of the energy is being added through condensation, and most of the energy is being removed through radiation. And sensible is kind of a smaller component. But if you look spatially, you see that the spatial structure of the dry looks a lot like the spatial structure of condensation. And so in the middle panel here, what I'm showing is the global anomaly. So this is the same plot as the left, but with the global means removed. And you can see that, in fact, the global anomaly from condensation that's almost on top of the global anomaly for the total heat input in the gray. And so what you can do is you can use these global anomalies to calculate an implied heat transport, which is what this formula is showing here. Basically, you take each of these components separately and say, okay, if all of the heat was coming from this one source and it was balanced by a globally uniform source or sink, that would basically give you my global anomaly. And I could treat those global anomalies the same way as a total and integrate them. And so each of these components here on the right is the heat transport that's implied just from one physical process. So the purple line here is the heat transport needed in the atmosphere to actually balance the condensational heating that's happening in the atmosphere. And so what you see is that you get really large polar transports implied by condensational heating. So especially in the tropics, you get these big peaks that are moving polarwards. And you see that a lot of the dry heat transport, even though we call it dry heat transport because of the heat transport of dry air, it's actually coming from condensation. So really, moist processes are actually, because they're adding so much heat to the atmosphere in this very heterogeneous way with a lot of spatial structure, a lot of the atmospheric heat transport of dry air actually exists to balance the energy input from condensation. And you see that the purple line and the gray line kind of match up. So a lot of the heat transport, especially out of the tropics, is really being driven by condensation directly. I'm not going to talk about it in this talk, but you can actually do some experiments with some idealized tracers that follow heat around as it's produced. And you can actually show that those tracers follow these same curves. So it's not just a mathematical construct. At least in some models, you can actually follow this heat transport and find that it matches. Okay, so that was just the dry component, but we can do the same kind of decomposition with the total energy input as well. So this black line is the same as what I was showing on the previous slide. This is the total energy input into the atmosphere. And if you do the budget for the total energy input, you have energy inputs from evaporation, sensible heat flux of the surface, and also the radiation. And kind of similar to the previous case with the dry, where it was really condensation that was looking like the total, you get a similar story here. So on a global scale, evaporation roughly balances radiation. So a lot of the energy being added to the atmosphere comes from evaporation, and most of the energy being removed from the atmosphere comes from radiation. But if you take out the spatial means of these and look at the global anomalies, you see that, kind of similar to the previous slide again, that the global anomaly of the total looks a lot like the global anomaly just coming from evaporation. And this means that if you were to integrate these things and find the implied heat transport, you get that the implied heat transport from evaporation looks a lot like the total atmospheric heat transport. Or in other words, the green curve here matches pretty well to the total black curve. And again, this is coming from the fact that most of the spatial structure is in evaporation and not very much of it's in the radiation. And so kind of the way you can think about this is that we have this solar insulation coming at the top of the atmosphere. A big chunk of it gets absorbed by the surface, and the surface has to somehow put that energy back into the atmosphere. One of the main ways it puts energy back into the atmosphere is through evaporation. And because of the Clausius-Capurian relation and these temperature gradients in the surface, get really magnified. And so evaporation has a very strong radial structure to it. You can really see that in these gradients, the green curve on the left. By contrast, radiation doesn't have nearly that same spatial structure. So when you look at the anomaly from evaporation really dominates over the anomalies from radiation or sensible. And that's why the total atmospheric transport looks so much like what's coming from evaporation. There's a second way we can think about this, though, which is how the heat transport that we've calculated in this green curve coming from evaporation is really combining two different components. So now what I'm showing is just the implied heat transports for what I'm calling the moist-dry perspective, which is sort of the standard picture. And the blue curve is showing the transport of water vapor or heat transport from water vapor. In gray is showing the heat transport from dry air. Black is the total. In the middle, I'm showing just the decomposition of the gray curve. So this is, you can think about it as a dry static energy decomposition. You see the gray curve there. Again, the purple curve is what's coming from condensation. And on the right, we can do what we're calling the moist static energy decomposition, where we decompose the total. And now the decomposition is between evaporation, sensible, and radiation. And you can see that the green curve looks a lot like the black curve. Okay, so if you break out the energy budgets for each of these components, you can kind of think about the total energy budget in two different ways. So the standard approach is to separate the energy budget into a moist term and a dry term. And so the moist term you can think about as E minus P, and the dry term combines the latent heat coming from condensation, which, if you make some approximations, is basically equal to the latent heat times the total amount of precipitation in the column. And the sensible heat flux and the radiation. So these are the different components of dry. In the MSC decomposition, we just have the latent heat coming from evaporation, the sensible flux, and the radiation flux. And so what the MSC decomposition has done is it's separated out the different components in the dry and then combined the moist and precipitation component together into one evaporation component. And so in other words, what we've done by calculating the heat transport implied from evaporation is we've combined two different transports together. We've combined one transport, which is a transport of water vapor in the blue curve here, and a second transport, which is the transport of dry static energy coming from condensation, which is the purple curve here. So the curve on the right is actually the sum of the blue and purple curves. So by finding the heat transport implied by evaporation, we've combined the two different heat transports associated with different parts of the energy cycle corresponding to the water cycle. So the first part is adding water vapor to the atmosphere that then moves around. That's the blue curve. The second part is the energy in the dry air that's left after that water vapor condenses. That's the purple curve. And so by finding the implied heat transport of evaporation, what we've really done is found the heat transport associated with the cycling of the hydrological cycle and the cycling of water vapor through the atmosphere. And what you see is that it's really the cycling of water vapor through the atmosphere which really drives total heat transport. So without and I'll show this more explicitly in the next section, but without the cycling of water vapor through the atmosphere, the heat transport would be completely different. And in fact, you can go to some very extreme cases and show that without the cycling of water vapor through the atmosphere, there would be almost no heat transport in the atmosphere. So really, it's the water cycle is actually the thing that maintains atmospheric heat transport and really drives it. Okay, so to quickly summarize, so we have this new implied heat transport perspective, which gives us a physical decomposition of atmospheric heat transport and lets us divide it by the different physical processes which add and remove energy from the atmosphere. I've shown that the implied heat transport coming from evaporation is really similar to the total atmospheric heat transport. And also importantly, it removes this decomposition between the dry and the moist. And a big part of that is because where you have condensation, that condensation is a negative term in the water budget, but it's a positive term in the energy budget. And so by basically adding those two components together in this green curve here, we've removed all these different compensations that are coming because of having a positive term in one budget and a negative term in the next. Okay, so now we're going to turn to some model experiments and ask how evaporation can kind of couple oceanic and atmospheric heat transport together. Okay, so to start off, I'm going to show, this is a very simple model. This is a gray radiation aquaplanet. It's the one's familiar with these. And this is a similar decomposition to what I had on the previous slide. Black's in the total. The heat transport implied from evaporation is in the green, and you can see that it matches with the total pretty well. What I've done on the panel on the right here is I've added just a very simple representation of ocean heat transport. So I've basically put in like the heat transport corresponding to something like a subtropical cell. And what you can see is that that heat transport in the ocean is compensated by a decrease in heat transport in the atmosphere. And that decrease in atmospheric heat transport comes almost exclusively through evaporation. So when we change the ocean heat transport and the ocean heat uptake, that has the effect of changing evaporation, which changes the atmospheric heat transport. We've done this in a much more sophisticated model as well. So this is a coupled aquaplanet model. These are some simulations. This is a new setup developed by Zoe. And what she's done is she's taken MOM6 and coupled it to AM2 in an aquaplanet configuration. So there's no land anywhere. It's all ocean except for at the poles. She has to put in 2 land caps in order to keep the numerics running stably. That's these kind of gray bars here. But over the rest of the planet, it's just a global ocean. But it's a fully parameterized atmosphere and a fully parameterized ocean. And so you can see now you get much larger ocean heat transport in the model when the ocean has its own dynamics and it's allowed to do whatever it wants. So you get pretty strong ocean heat transport in the tropics. Again, there's no land. And then atmospheric heat transport, but most of the atmospheric heat transport is still being driven by evaporation. Something that's really cool about this model is that you can add little strips of land. And if you add little strips of land in exactly the right way, you can switch from having an aquaplanet configuration to having an AMOC planet configuration. A little too much to get into how that works now, but what's cool is that when you add an AMOC, you really change the ocean heat transport. And in response, there's a big change in the atmospheric heat transport that comes along with the change in the ocean heat transport. So that's what's showing here. So the teal curve is the change in ocean heat transport that you get by adding an AMOC, and the black curve is the change in atmospheric heat transport you get when you switch from an aquaplanet model to an AMOC model. And what's interesting is that this green curve is the heat transport implied by evaporation. So just by adding an AMOC into our model and shifting from an aquaplanet to something that has an AMOC and more extratropical heat transport as well, the primary way that's communicated to the atmosphere is through evaporation. So when we start changing ocean heat transport, we also start getting a related evaporation change. And that related change in evaporation is the thing most responsible for changing the atmospheric heat transport, which is really interesting because, originally we had kind of thought that, the results I was showing on the previous slide were just a tropical phenomenon, right? There's a lot of evaporation in the tropics and subtropics. So obviously, if you change ocean heat transport there, you're going to get a resulting change in atmospheric heat transport. But a lot of the changes we get on what I'm calling here AMOC planet are actually extratropical. So you get big changes in the subpolar gyres, especially in this setup, the narrow basin. And what's interesting is that those changes in the ocean heat uptake and ocean circulation are still communicated to the atmosphere primarily through evaporation. So wherever you have the ocean changing, you have the surface fluxes changing, mostly evaporation, which then has the effect of changing the atmospheric heat transport. So another way to put this is that evaporation is really mediating the response of the atmosphere to the ocean. So whenever you start changing the ocean, you get these changes in evaporation, which mediate those changes back to the atmosphere. And so we wanted to kind of test this idea more directly. So here what I'm doing is I'm starting with the same gray radiation aquaplanet and just asking, okay, well, what would happen if you just reduced evaporation, right? Because our whole hypothesis up to this point is that evaporation is really the thing driving atmospheric heat transport. And so you could just ask, well, what would happen if we just artificially reduce the amount of evaporation in a model? Could we get a corresponding decrease in the amount of atmospheric heat transport? And if you look, you can see that's what happens. So on the left, again, I have the same gray radiation aquaplanet. And on the right, what I've done is I've just gone into the code and I've added a factor of 0.5 in front of everywhere that evaporation gets calculated. So instead of getting the normal amount of evaporation that would be calculated in the model gets approximately half of what it would normally see. And when you do this, you get different heat transport. So you can see that the total heat transport, well, actually, first let me say that when you do this, you don't actually reduce evaporation by half. You reduce it by a factor of closer to 10%. Because what happens in this model is that the model actually responds by cooling significantly. So when you reduce evaporation, you put less water vapor into the atmosphere, and because of the water vapor feedback, the model actually cools quite significantly. And this cooling of the model actually offsets the change in evaporation that you've put in. So as a consequence, you get much less than a 50% change in evaporation. So it makes sense that our change in atmospheric heat transport isn't a 50% change, quite a bit smaller. And you see what happens is that you get these big changes in evaporation, especially around the boundary between the subtropics and extratropics. And those big changes in evaporation cause a decrease in total heat transport. Interestingly, though, you get an increase in the sensible and the radiation that try to compensate for this decrease in evaporation. And the way to think about this, I think, is that when you have less energy coming out of the surface, one way that the surface tries to respond is by increasing the sensible and radiative fluxes that would normally be balanced by a bigger evaporation. And so that's why you have these compensating heat transports coming in the opposite way. But either way, the overall story is you cut down on evaporation in the model and you reduce the total heat transport of the atmosphere quite significantly. So the next question is, okay, well, what would happen if you tried this in the coupled model? And so here I'm showing the coupled aquaplanet model again. On the left, this is the same control figure that I had before. And on the right, this is showing the same experiment that I just showed with the gray radiation model. So what we've done is we've gone back into the code now for the coupled model, and we've reduced the factor in front of evaporation by half. And so we've essentially reduced how efficient evaporation is at taking heat from the surface and putting it into the atmosphere. And so the results are a little messy, but what you get is a decrease in ocean heat transport near where the peak of ocean heat transport is. So the peak ocean heat transport actually decreases by about 0.3 petawatts. And the maximum heat transport actually decreases, or sorry, the ocean heat transport increases by about 0.3 petawatts where the maximum is. And the atmospheric heat transport decreases by about 0.4 petawatts near where the maximum in atmospheric heat transport is. And so by decreasing the amount of evaporation, we basically changed the partitioning of heat transport. So more heat transport is being transported in the ocean now, and less is being transported in the atmosphere than before. Another way to think about this is at the beginning of my talk, I was talking about how evaporation takes energy out of the surface and puts it into the atmosphere. And since evaporation is strongest in the subtropics, you expect where you have a lot of evaporation to be taking a lot of energy out of the ocean and putting it into the atmosphere. So if you reduce the efficiency of evaporation, what you've done is you've left more energy in the ocean and less in the atmosphere above. And so this changes the partitioning of heat transport. So you get overall more energy in the ocean, or being moved further polewards by the ocean, and less energy being moved further polewards by the atmosphere. Interestingly, again, you see the same compensation between evaporation and the purely dry components that we got before. So again, where we have, you would expect from just the changes in evaporation alone, you would actually get much stronger decreases in total atmospheric heat transport than what you get. But there's some compensations by the dry components that actually act to increase atmospheric heat transport going forward. And so something that's really interesting to me is, my first expectation was that if you just decrease evaporation, you'd expect to see a big decrease in the transport of moisture through the atmosphere. And that would explain basically the total decrease in atmospheric heat transport. That's not actually what happens. So on the left here, I'm showing a similar breakdown to before. These are just the responses now to the change in atmospheric heat transport. And so you see that this is showing the dry and moist decomposition. and you see that there's this big spike in the gray and the blue. That corresponds to a shift of the Hadley cell. So when you decrease the evaporation, the Hadley cell actually contracts a little bit, and that contraction is basically shown by the edge moving inwards, which looks like this spike in heat transports. And so you get an increase in the moisture transport where the new edge of the Hadley cell is, and an increase in the dry transport where the new edge is. Okay, but if you look in the extratropics, something really interesting is that you see that blue curve is basically 0. So the response of moisture transport in the extratropics is very small, which is interesting because the total heat transport is still pretty large, but most of the total heat transport is actually coming from the dry component. And so we can use this kind of decomposition method with these implied components to separate this out and see why this is happening. And if you do that, what you see is that most of the change in the dry component is actually coming from a change in condensation. So because there's less water vapor in the atmosphere, there's less condensation happening as well. And so that decrease in condensation is actually why there's less dry heat transport. And because there's almost no moist heat transport, this decrease in condensation is actually why there's less overall heat transport in the extratropics in this model. So decreasing evaporation, in this case, doesn't actually change the extratropical moisture transport that much. What it does is decrease extratropical condensation, which has the effect of decreasing extratropical dry static energy transport. And I think this is something that needs to be thought about more, because what it's saying is that a slowdown of the hydrologic cycle actually changes the dry atmospheric heat transport more than it does the transport of moisture. In other words, it's wrong to think that just changing evaporation at the surface is going to necessarily change the transport of moisture in the atmosphere. It will change how quickly the cycling of moisture is happening through the atmosphere, though. And in this case, by changing that cycling, it actually has the effect of changing the other component of the heat transport, which is the dry static energy coming from condensation, this purple curve. And it turns out, at least in this configuration, that effect actually dominates more. This also has really interesting implications for what moisture transport looks like in this model. Since evaporation is going down and the total transport is also decreasing, what that's saying is that there has to be more precipitation coming from local sources. So you would expect in this, I haven't done these calculations explicitly, but you would kind of expect in this model that the transport distance of water vapor goes through is decreasing, which is also really interesting. And so one question that I had for a while I've been able to recently answer is, how far can we push this? So, with these experiments, we've been putting this kind of weak change to evaporation and then looking at the effects of partitioning and the hydro. But you might be interested to see if we can push this all the way. So here are two simulations I got from this paper by Horner et al. And these are neoprotezoic experiments. So they're experiments with relatively high CO2 values, but relatively low insulation values. But they're set up kind of similar to the models I've been showing before. They have a slab surface, and then a slab ocean surface, and then an atmosphere above. So they're kind of like aquaplanet models. On the left here is showing their control simulation, which does something kind of similar to what I was showing. And on the right, what they do is that they drive the model into a snowball simulation. So they change the CO2 and insulation sufficiently enough that they're able to cover the entire planet with ice. And when you do this, you almost completely shut off evaporation because you have a very cold ice surface that's hard to evaporate from instead of a warm ocean surface that's very easy to evaporate from. And when you do this, you can see that the total atmospheric heat transport decreases to almost nothing. Actually decreases by about a factor of 10 between the control and the snowball. And this is really interesting because it kind of suggests that when you reduce the atmospheric heat transport from evaporation in these kind of weak perturbation experiments, you see that you get this response from the sensible and the radiation, but the response from the sensible and radiation isn't enough to fully compensate from evaporation. But in these very large perturbation experiments, what you see is that, yeah, you still get a response, particularly from the sensible in this case, but it's not nearly enough to compensate for the reduction in heat transport that you get from shutting off the hydrologic cycle. So there are some compensations that can happen from the sensible to overcome these perturbations to evaporation, but they're not nearly enough to sustain the same magnitude of atmospheric heat transport that the hydrologic cycle is able to sustain. And lastly, I'll just show these results. These are some CO2 doubling experiments. So on the left, this is a gray radiation aquaplanet, and on the right, this is a CAM4 slab ocean simulation. And what you can see is that when you do a CO2 doubling, you get these compensating moist and dry changes. So I'm showing the moist in the blue, the dry in the gray. I'm also showing the condensation, which is in the purple, and you can see a lot of times you can't even see the gray because the change in condensation is lying almost on top of it. So in other words, what this is saying is that when you double CO2, you increase the strength of the hydrologic cycle in these two models. And when you do that, you increase the moist transport. You also increase the amount of condensation in the atmosphere. And this increase in the amount of condensation drives a corresponding increase in DSE transport. And when you take the difference between those two, you get this black curve, which is the total heat transport. And so there's been a lot of papers, including some that I've contributed to, that have talked about the kind of compensations between the dry and moist component in understanding the total heat transport that we get in response to increasing CO2 simulations. However, if you were to look at this from an evaporation perspective, what you get is you can actually eliminate this compensation altogether and just look at how much evaporation is changing at the surface. And just from knowing how much evaporation is changing at the surface, you can estimate fairly well the total change in heat transport in both of these simulations. And so this is kind of a different way to think about it. Rather than thinking about the total atmospheric heat transport as being this kind of small residual between dry static energy export and moisture transport, we can think about the total atmospheric heat transport as being driven mostly through evaporation, which just requires us to think about what's going on at the surface fluxes. The disadvantage is that in an evaporation lens, you don't learn anything about this blue curve, which is of interest all on its own, right? You know, we're interested in how moisture is transported in the atmosphere when we think about changes in precipitation and hydroclimate. So, you know, this blue curve is very important in its own right. But if we just wanted to know total atmospheric heat transport and the response of that to increases in CO2, it's actually much easier to think about that from a surface flux perspective and just ask how evaporation is changing, rather than trying to come up with some theory that explains why the compensation between moist and dry look the way that they do. Okay, so that was a lot, but to summarize quickly, we've seen that evaporation removes energy from the ocean and adds it to the atmosphere, and this really couples ocean heat transport and atmospheric heat transport together. In particular, if you have tropical or subtropical evaporation, this increases atmospheric heat transport and decreases ocean heat transport. And something that I think is maybe counterintuitive at first, but we can explain now, is that slowing down the hydrologic cycle has this effect of changing the dry atmospheric heat transport as well. So when we start looking at hydrologic cycle changes, we shouldn't just think about changes in moisture transport, we should also think about changes in dry static energy transport as well. And so lastly, I'd just like to ask this question: how well do we know global evaporation? And what can this tell us about our model biases? So at the start, I showed you one picture of the energy cycle where there's just one value for evaporation. But it turns out that actually we have a lot of trouble figuring out, even at the global scale, what evaporation should be. So here I'm showing first, these are global estimates of the surface energy budget. So each of these black dots is one CMIP5 or CMIP6 model, globally averaged. On the x-axis, I'm showing the turbulent flux. So this is the sum of the sensible and latent flux coming out of the surface. And on the y-axis, I'm showing the radiative flux. So this is the sum of long wave and short wave going into the surface. And this green line here corresponds to where a point would land if it has an ocean heat uptake of 1 watt per meter squared. So you can think that the global energy balance is the difference between the radiative and turbulent components. And this green line shows an ocean heat uptake of about 1 watt per meter squared. And you can see that most of the models do something about right, or something about 1 watt per meter squared, which is pretty similar to what you get when you look at Argo floats, for instance. But they disagree a lot on whether that 1 watt per meter squared is a compensation of 2 smaller components or 2 larger components. And so some models think that there's not that much radiation going into the surface and not that much turbulent flux leaving the surface. And some models think that there's a lot of radiative flux going into the surface and there's a lot of turbulent flux coming out of the surface. And you might say, okay, well, that's interesting that the models have this spread, but what do observations do? And so here in this purple cross or purple X here, estimate, this is combining OA flux, which is direct measurements of turbulent fluxes, or attempted direct measurements of turbulent fluxes, combined with the series satellite radiation of the surface. And you can see that they don't line anywhere near this 1 watt per meter squared line. They lie somewhere off. In other words, if you were to just use our direct observations of OA flux and series together, you get an ocean heat uptake that's greater than 15 watts per meter squared, which is much larger than anything observed. So our estimates of the turbulent flux and radiative flux are actually inconsistent with each other. They don't agree in terms of having something close to a closed energy budget. And this problem has been recognized for a long time. There's this review paper in U. But it kind of shows that we have this problem with the surface energy budget, and we can't directly close it from observation. And if we think what this means for the water cycle, it also implies that there's a huge spread in what the strength of the global water cycle should be. So before we were looking at the turbulent flux, which included evaporation. So there's some models that have a lot of evaporation, or a lot of turbulent flux, which means a lot of evaporation. And those models also have to have a lot of precipitation. So they lie up here. So what I'm showing now is a similar picture. On the x-axis is evaporation. The y-axis is precipitation. And if you're not changing the amount of water being stored on land that much, you should get that globally evaporation minus precipitation should be about 0. And so all these points should lie on about 1-to-1 line if they're conserving water, which most of the models do. You can also ask what observations are doing. So if you take the series data, you can say, okay, well, if I know how much ocean heat uptake there is, and I know how much radiation is going into the surface, then I can figure out how much turbulent flux is going out of the surface. And if I make some assumption about how much of that is going into sensible and how much of that's going into evaporation, on a global scale, I can use my radiation measurements to make an evaporation estimate, which is what this cross is here. So this is showing a series radiation estimate, sort of an indirect estimate of evaporation, combined with GPCP, which is satellite precipitation measurements. And you can see kind of similar problems that we had with the energy balance. We're not conserving water directly from these two observational estimates. However, if instead you use GPCP and combine it with the OA flux data, and I should say I've also used, so this is global evaporation, I've also used ERA 5 to fill in what's going on over land. But it turns out it doesn't really matter too much what you use over land. It's a much smaller component. So if you combine GPCP and OA flux, you get this purple cross here, which is pretty close to the 1-to-1 line. So it's kind of interesting because it says that if we were to just look at GPCP and OA flux, you would say, oh, okay, we have pretty good observations, roughly conserves models, or so roughly conserves water, but all the models are really biased, right? All the models are showing way too much evaporation, way too much precipitation compared with our GPCP OA flux. To put this in relative terms, we expect from most of our models about a 2% increase in global precipitation per degree Kelvin of global warming. So a 2-degree warming scenario corresponds to about a 4% increase in precipitation. The spread in models that I'm showing here is like a 15 to 20% spread. So there's, the spread in present day precipitation is many times larger than the projected increases in future precipitation under a lot of common global warming scenarios. But if we were to just look at the energy cycle, we see, and as I've said a few times now, evaporation is really important in linking together heat transport in the atmosphere and ocean. And so if you look at where these evaporation biases are occurring, so here I'm showing ERA 5, 2 CMIP generations in the red and green, and then away flux in the blue. And you can see that most of these evaporation biases are in the subtropics. And so, a hypothesis you might get from this is that there should be a bias in the atmosphere, in the partitioning of atmosphere and ocean heat transport corresponding to this bias in subtropical evaporation that we see between OA flux and the models. And that's basically what you get. So here in black, I'm showing the total heat transport. In red, I'm showing the atmospheric heat transport. And in blue, I'm showing the ocean heat transport, and the solid lines from the observations and the dashed lines from the models. And one quick comment I'll just make about the observations. Because the surface energy budget doesn't conserve energy, we can't use the surface fluxes directly and integrate them in order to get the ocean heat transport. So what we actually do is we take TOA measurements from satellites to estimate this black curve, the total heat transport, and then we take estimates coming from atmospheric reanalysis to get the red curve here, and then we use the difference between the two to get the ocean heat transport. And this strategy has been used for a while. I think Tremberth and Caron was one of the first. So you can see, but here what's important is that you see that in general, the models have too much atmospheric heat transport and too little ocean heat transport. And here I've combined CMIP 3, 5, and 6. And you might think, well, maybe this is just a problem with older models and newer models have fixed it. But you can look across generations. My slides like this. There we go. So this is CMIP 3. So on the right here is showing the ocean and the atmosphere. And you can see that each of these individual models is one of these dotted lines. But you can see that the CMIP 3 mean is significantly above observations in the atmosphere, below observations in the ocean. Go to CMIP 5, very similar picture. CMIP 6, still a very similar picture. So across 3 different CMIP generations, we have this very persistent bias where there's too much atmospheric heat transport and too little ocean heat transport. So you might say, well, maybe it's not a problem with the models, maybe it's a problem with observations. So here what I'm showing is a whole bunch of different observational products. So in each of these dashed lines are the same, and the solid lines are actually slightly different. So on the left, this is what's showing if we use different top of atmospheric radiation products. So if we use series EBAF versus ERBI radiation versus the series SSF radiation, and you can see that it does not change the observed heat transport all that much. You can also ask what would happen if we put in different atmospheric reanalyses. So on the top right, this is showing series EBAF and then using ERA interim instead of ERA 5. In the middle is showing series EBAF and using the NCEP reanalysis instead of ERA 5. And there's some slight differences. You can see there's this little kink in the NCEP reanalysis that you don't get in the ERA interim reanalysis or the ERA 5. But in general, it's pretty similar. And then lastly, you could say, well, maybe this is just an issue with observations of ocean heat uptake. If there's a strong meridional structure to ocean heat uptake instead of something just total uniform, maybe that is the issue. And so what we've done here is we tried to account for that. So this blue line is showing the implied ocean heat transport, which comes if you just imagine a globally uniform ocean heat uptake. And the cyan line here is showing what would happen if you put in an ocean heat uptake corresponding to the EN4 data, which comes from Argo. So if you used actual observations of ocean heating to figure out what the ocean heat uptake is, put that in, and you can see that these lines lie almost on top of each other. So there's virtually no difference. And so, the big takeaway from this is regardless of what observational products we use or what generation of models we look at, there's this very robustness to the result that very consistently models have too much atmospheric heat transport and too little ocean heat transport. And if you think about the evaporation biases, this is entirely consistent. So models have models have too much subtropical evaporation relative to OA flux. So in other words, the models are taking too much energy out of the ocean and putting it into the atmosphere in the subtropics. And if you think about what that does to the heat transport, that means there's going to be less heat transport in the ocean and more heat transport in the atmosphere. So this incredibly persistent partitioning bias in heat transport that we see also matches a very persistent bias in evaporation that we see across model generation as well. And to demonstrate this, what we've done here is we've gone, I know this plots are a little messy, but we've looked at the implied heat transport bias in the ocean and the atmosphere. So on the left, this is showing the atmosphere, and on the right, the ocean. And this green curve is what you get if you calculate the implied heat transport bias. So using the global heating anomaly from the models, and subtracting off the global heating anomaly from the OBS, and then using that to find an implied heat transport bias. And if you do this using modeled evaporation compared with OA flux evaporation, you get this green curve. And so you see that the bias in atmospheric heat transport matches pretty well with the bias implied just from the bias in evaporation. So the fact that the models have biased evaporation implies that they have biased atmospheric heat transport as well. And you can do the same thing in the ocean because evaporation is taking energy from the ocean, putting it into the atmosphere. This green curve is now flipped. So your negative AHT biases are positive OHT biases. And you see that in the northern hemisphere, actually a lot of the model bias is coming from evaporation. So just the fact that the models have biased evaporation explains a lot of the partitioning bias between the ocean and the atmosphere, comparing models to OA flux. If you look at the southern hemisphere, it looks like something else is going on. So the models have part of the story is evaporation, but it looks like the radiative fluxes are also playing a big role in the southern hemisphere. We think this might be related to a shortwave cloud bias, but I'm not totally sure, and I'd be happy to hear people's thoughts about this. But yeah, the big takeaway is that if we just know the evaporation biases in the models versus the observations, we can actually figure out what these heat transport biases are, which is good because there's this incredibly persistent heat transport bias, and there's also been a very persistent bias in evaporation. So by linking the two, we're hopefully able to explain it and maybe make some improvement on the model. All right, so just to conclude from these three different parts of the talk, so in the first part, I talked about how the atmospheric energy balance is largely between evaporation and long-wave cooling. And because evaporation has so much meridional structure to it compared with the other terms in the budget, it really dominates the total. And so almost all of the atmospheric heat transport is being driven by evaporation. In part two, with these different model experiments, I showed how evaporation really couples atmospheric and ocean heat transport together and really mediates the response of the atmospheric heat transport to different perturbations, whether that's through CO2, directly perturbing the evaporation, or going out in the ocean. And then the third part, I show that there's this very persistent evaporation bias and these really persistent atmosphere and ocean heat transport biases as well. We've basically been able to link these two together. I think one way to think about this is that there's kind of two camps of data. So there's data which looks more like OA flux and GPCP and satisfies those global budgets. And then there's data that looks more like series and satisfies that global budget. And the models have too much evaporation for OA flux and GPCP, but they tend to kind of cluster around the series data. So I don't fully know which one of those two is right, but at least in thinking about the heat transport, it looks like the OA flux numbers make more sense for heat transport. Yeah, so I think I'll wrap up there, and thank you very much.
Thanks so much, Robert. I think we have about 5 minutes left for questions. If people want to take a moment to enter their questions into the question panel, or you can use the raise hand feature within GoTo, and I can unmute your microphone so you can ask your question directly. Robert, also, if you'd want to enter your email into the chat just so people can see it and follow up, if you'd like to do that as well. I'm gonna take back the mic or the mouse.
And moisture transfer.
Claire, I have a question.
Yeah, it's Jenny.
A question from the group. So this is a question from Matt Newman. Has he looked at the interaction of the winds and moisture transport and evaporation?
Not as much as I would like. So I can say that in these experiments where we just reduce the evaporation coefficient, it seems like the primary response isn't through the winds, it's actually through the temperature. So, or in other words, when you change the evaporation coefficient, you get these big compensations that compensate for the change you put in. And most of those compensations come from changes in surface and atmospheric temperature and not from changes in wind. I mean, a big fraction of observed variability in evaporation does seem to be coming from the winds. But I haven't yet found a model where I've nudged something that wasn't the winds and then seen a response in the winds coming out. But yeah, this is very high on my to-do list of things to look at because I think it's really important.
Thanks. We have another question from Kirsten Findell. Can you talk about how land complicates this ocean-driven perspective, especially how soil moisture limitation restricts evaporation?
Yeah, so there's a couple things to say. So one thing is that because in general the ocean is much wetter than the land, pretty safe assumption most of the time, the land doesn't play a bigger role in evaporation. And so because of that, actually a lot of the hemispheric, so let me see if I can go back a couple slides.
Sorry, let me give you.
Oh, no, that's fine, don't worry about it. You can kind of see it in the top picture on the left here. Oh, now it's going back. Well, anyways, you can see it in this top picture on the left here, that the cross-equatorial heat transport implied by evaporation is pretty far northward. That's actually almost entirely because of the distribution of land in the atmosphere. Actually, I might. Yeah, here we go. Okay, so on the bottom, this is showing an aquaplanet radiation, and on the right, this is what we call northwest land. So this is an aquaplanet, and we've just stuck in a giant chunk of land in the northwest top quadrant. And what you see is that you get really different cross-equatorial heat transport. You get much more evaporation driving heat transport across the equator, and you get compensations from the sensible and the radiation component going back across the equator in the other way. So actually a lot of in other words, like a lot of the hemispheric asymmetry we see in atmospheric heat transport is coming from the presence of land. And it's as you said, because evaporation over land is moisture limited, and so you just don't have as much evaporation over land. And it turns out that's all you need to explain the hemispheric asymmetries in atmospheric heat transport. You don't need clouds, you don't need sea ice, you don't even need to have the right distribution of land. Just sticking a block of land in the northern hemisphere is enough to give you this hemispheric asymmetry.
Great. I think that just about wraps up our time limit for today. I want to thank you again for being the first in this series, Robert, and thank you all for joining us today. And we'll stay tuned for our next webinar, which is going to happen on October 31st. And we'll be sending out some information on that. Ginny?
Hey, Clara, Can we have time for one more question?
Sure, let's sneak one in.
It's quick. I know you showed the INSEP reanalysis, but do you have an idea of how well these partitioning of important quantities are represented in NOAA's operational model?
I don't, sorry. But I'd be very curious to find out. And yeah, if anyone has any other questions, please feel free to send me an email. I'd love to talk more about them.
Okay, great. Thank you all again. That wraps up our webinar. We will be recording it, and we will be figuring out how to post that afterwards. So thank you again, and have a great day.
Thanks, everyone.